Today, I'm going to talk about, yet again, the algorithm Q sigma, which is an algorithm for reinforcement learning that unifies both Sarsa and expected Sarsa. We already have a AAAI paper on this algorithm, and by we I mean Chris and Zach and me, along with Rich. And in that paper, we just found that Q sigma works pretty well in the tabular case and the linear function approximation case. So I was wondering whether we would find similar results in the nonlinear function approximation case. For that reason, I decided to combine the architecture DQN with Q sigma just to see how that would work. Now, this is how my talk is going to go. First, I'm going to introduce Q sigma and how to extend it to the n-step case. Second, I'm just going to talk about the DQN algorithm and how to change it in order to implement the deep Q sigma network. And finally, I'm just going to present some experimental results in mountain car using the deep Q sigma network. OK, so let's start from the beginning. In the reinforcement learning framework, we model the sequential decision process as a Markov decision process. In this framework, we have an agent, which is both a learner and a decision maker. And we have an environment, which represents everything external to the agent. It basically represents the world. The agent and the environment interact over a sequence of discrete time steps. At every time step t, the environment sends information to the agent in the form of a state. And the agent uses this information to take an action, which it sends to the environment. The environment, in return, sends back a new state and a reward. Now, states follow a probability function, p, and actions are selected according to a policy, pi. The goal of the agent is to maximize the amount of reward that it gets over time. And for this goal, it is often useful to have some notion of how much reward we are going to get as a function of the state and action. And for that reason, we use action value functions. So basically, action value functions tell us how much reward we're going to obtain in the future, given our current state and action. They are denoted as q pi of state S and action A. And they are defined as the expected value of pi, the expected value with respect of the policy pi, and the transition probability function p of the sum of rewards, discounted by some factor gamma, which is between 0 and 1. And that is conditioned on the current state being S and the current action being A. Now, we often write that sum of reward up there like this, just to make it shorter. And we call this quantity the return, or discounted return. Now, in order to estimate action value functions, we use temporal difference learning methods, which use update functions such as this one. Our new estimate of the action value function, qt plus 1, is going to be defined as 1 minus alpha times our old estimate plus some estimate of the return. Now, alpha here is just a learning rate parameter that controls how much learning is going to happen over time. And this quantity right here, g hat, is just the best guess that we have about how much reward we're going to get in the future. Now, a different way to write this update function is like this. In this case, this quantity in brackets is called the TD error and is denoted delta t. Now, this g hat, the estimate of the return, characterizes every temporal difference learning algorithm. So for example, if we want to do Sarsa, we will write g hat like this, where it's just the next reward and some sample of the next action value function. Now, update functions can be represented graphically by using backup diagrams. Here, I'm going to do it for Sarsa. So we take the initial state and action pair, and we represent that as a solid circle. Then we take the next reward, and we represent that as an arrow pointing towards the next state, which is represented as an empty circle. And finally, that state leads to another action, which is represented as another solid circle. Now, backup diagrams are very helpful to introduce algorithms in a very intuitive way. And we can use them to represent many other algorithms. So for example, for expected Sarsa, we can also do the same. The backup diagram looks like this. But in this case, these 3 arrows at the bottom represent an expectation taken over all the actions. We can do a similar thing for Q-learning. The backup diagram looks like that. And this arc connecting the arrows represent a maximization taking over all the actions. So now, Oh, Q-learning is just a special case of expected Sarsa, so I'm just going to omit it for the rest of this section of the talk. Now, how does the backup diagram for Q sigma look like? Well, we start our initial state action pair. And remember, Q sigma unifies both Sarsa and expected Sarsa, and the parameter sigma lets us choose whether to do one or the other. If sigma is equals to 1, we are just going to go down the Sarsa path, and we are just going to compute the Sarsa back update. If sigma equals to 0, we are going to go down the expected Sarsa path, and we're going to compute that update. However, nothing in this theory stops us from choosing sigma anything between 0 and 1. In that case, we are actually taking a weighted sum of both Sarsa and expected Sarsa. Now, this dashed line just represents that these two states right here are actually the same. So the initial state is just the state at the top. And these states at the bottom, this one over here and that one over there, are also the same state. So I'm also going to join them with a dashed line. It's just to emphasize that they are the same. Now, all of these algorithms can be extended to the n-step case, where instead of looking one step into the future, we're going to look n steps into the future. For Sarsa, this is straightforward. For example, the backup diagram for 3-step Sarsa looks like this. We just look 3 steps into the future. And then we back up all that information back to the initial state action pair. For expected Sarsa, it generalizes to the tree backup algorithm, which looks like this. It's kind of like Sarsa, just like, but at every step, we take an expectation over all the actions. And we just do that 3 times. So now, how does the backup diagram for n-step Q sigma looks like? I'm just going to do the 2-step case. For the first step, we just take the regular 1-step Q sigma. And then at the next state, right here, the orange one, we're going to make the same decision again. We're going to choose whether to use Sarsa or expected Sarsa or some combination of the 2 of them. So it's just going to look like that. Now, if we fix sigma to be equal to 1, we recover n-step Sarsa. And if we choose sigma equals to 0, we recover tree backup. However, sigma doesn't have to remain constant throughout the backup. So we can change it over time. So for example, we can choose sigma equals 1 in the first step, then sigma equals 0, and then sigma equals 1 again. Or as another example is just, we can do this, for example. And this just shows that the flexibility that the Q sigma algorithm provides. We can represent all these family of algorithms just by introducing this parameter sigma. Now, you might be wondering, why use Q sigma at all? Why don't you stick to Sarsa or expected Sarsa, since they work so well? The reason for doing Q sigma is that in our AAAI paper, we found that sometimes intermediate values of sigma actually perform better than either of the extremes. And also, we found that decaying sigma over time from 1 to 0 actually resulted in the best performance in 3 different environments. Now, we tested this in 2 tabular environments and 1 continuous environment with linear function approximation. So I wanted to see whether this extends to the nonlinear case. And for that reason, yes?
Since you're going to move on to the next step, do you have any intuition about why it works better to decay from 1 to 0?
Yeah, the expected Sarsa, or the tree backup algorithm has a lot of bias because it's computing all these estimates over basically random values at the very beginning. So at that point, it's better just to do Sarsa because it's less biased. However, Sarsa over time has more variance, so it's better to use the tree backup algorithm later on because it becomes less and less biased, but it has lower variance. And that's why decaying sigma over time results in better performance.
I have a simple question about, I had that about already asked the first.
Yeah.
What about the first one? What about guys that aren't 0 or 1, but something in between?
Yeah. Well, we demonstrated this empirically. Intuitively, I really wouldn't be able to explain why.
Yes, you will, right? Yeah.
Hopefully, yes. Anyways, so I wanted to combine Q sigma with DQN to test the nonlinear function approximation case. Now, for DQN, at its core, is just a neural network that, yes, it's just a neural network, that looks at the current state and at the other end outputs the estimate of the action value function for all the actions given the current state. Now, if we want to combine DQN with Q sigma, there's a few things that we need to consider and that we need to change. The first one is the loss function, which looks like this for DQN. For now, just ignore deltas. So this one and this one, just ignore it. Because the thing that we need to focus on right now is that this quantity right here is just the estimate of the return used in the Q-learning algorithm. And this quantity in brackets is just the TD error. So essentially, the DQN architecture is just using the square TD error as a loss function and is minimizing that. Now, about the thetas right here, the reason why we use them is because each of them represents a different network that gives us different estimates of the Q, of the action value function. This one right here represents the target network, and this one right here represents what I call the update network. It doesn't actually have a name. The update network is updated at every time step, and the target network is updated less frequently. And the reason for doing this is that it induces a stability. Now, if we want to adapt all of this to the Q sigma, the only thing that we need to change is this one right here. Remember, every TD algorithm is characterized by their estimate of the return. So instead of using the one for Q learning, we're going to use the one for Q sigma, for n-step Q sigma. Don't worry about how to compute this. The equation gets very ugly very fast. But the important thing to note is that there are two parameters right here. One is sigma, and the other one is n. By changing these parameters, we are able to represent all the algorithms that I already have talked about before. And additionally, we're going to compute this estimate of the return using a target network. And just like before, the target network is going to be updated less frequently. Another algorithmic detail that we need to pay attention to is the experience replay buffer. So the DQN agent doesn't learn directly from observations of the environment. Instead, it stores those observations into a buffer. These observations consist of a state, an action, a reward, and an indicator variable that tells us whether that's a terminal state or not. Now, the problem that this poses for DQ sigma network is that this state and that action are sampled according to policy pi t. However, when we retrieve that state and action at time k, sometime in the future, we're going to be actually following the policy pi k. So, and there's no guarantee that pi k and pi t are going to be the same. So the problem is that if we use pi k to compute the estimate of the return, that estimate might actually be biased. Now, there's two approaches that we can take in order to solve this problem. The first one is a very well-known approach used in deep reinforcement learning, which consists of ignoring the problem and hope that nothing breaks. It's very common. Just read the Apex paper. Anyways, sorry. The second approach is more principled. I didn't want to throw anybody under the bus. The second approach is more principled. We're actually going to store pi t in the buffer, and we're going to use that pi t to compute the importance sampling ratio pi k over pi t. And we can use this ratio to correct for the differences in policies. If pi k and pi t are the same, this is just going to be 1, so nothing else is going to happen. But if they are different, this term is going to correct for that difference. And additionally, I'm also going to store sigma t, because for some algorithms that I'm going to show you, sigma is going to change over time. OK, and finally, the last thing that we need to consider is annealing epsilon. The DQN agent doesn't actually behave according to the policy whose values it is trying to estimate. It behaves according to a behavior policy, mu t, which is an epsilon greedy policy that, with probability 1 minus epsilon t, it chooses the action that maximizes the current estimate of the action value function. And with probability epsilon t, it just chooses a random action. Now, epsilon gets initialized at 1, and then it decays linearly over time towards 0.1. And that happens as t goes to h. H, in this case, is a hyperparameter called the exploration frame. And we can just set it to any amount that we want. Yes, so what kind of experiments I'm going to show you? Now we're on to the good stuff. The first one is going to be testing sampling from the buffer as if the observations were off policy against sampling from the buffer as if the observations were on policy. That means computing the importance sampling ratio pi k over pi t. For this experiment, I'm gonna try 3 different agents: a Sarsa agent, a Q sigma 0.5 agent, and a decaying sigma agent. Now, this decaying sigma agent is just a Q sigma agent, which parameter sigma gets initialized at 1, and then over time it decays exponentially towards 0 at a rate of 0.95. That means at the end of each episode, we multiply sigma by 0.95, and then over training, it eventually is going to reach 0. The next experiment that I'm going to try is testing annealing epsilon versus non-annealing epsilon. I'm going to do that for a Sarsa agent, a Q sigma 0.5 agent, an expected Sarsa agent, a decaying sigma agent, and a Q learning agent. And finally, I want to see what's the effect of n on the performance of the DQ sigma network. For that, I'm going to implement these 4 agents, Sarsa, Q sigma 0.5, tree backup, and decaying sigma. And I'm going to test values of n equals to 1, 3, 5, 10, and 25. Sorry, and 20. Now, there's a ton of hyperparameters that are involved in the deep Q sigma network. But the only thing that we need to note is that all those hyperparameters are going to remain fixed for all of these agents. The only 3 parameters that are going to change is the n parameter, the sigma, and for one special case, the sigma decay rate, which I'm going to change in one experiment. Everything else is going to remain the same. The network architecture that I'm going to use is just going to be a feed-forward neural network with 1,000 neurons. And all the agents are going to follow an epsilon greedy policy with epsilon equal to 0.1. Okay, and the environment that I'm going to use is just mountain car, where we have a car. The goal is to get to the top of the hill. The state is the position and the velocity. And the action is -1, which represents accelerating back, 0, which represents coasting, and 1, which represents accelerating forward. The reward is always -1 at every time step, and it's just 0 whenever the agent reaches the very top. Now, an additional thing that I need to implement for this is if the agent ever spends 5,000 time steps in the environment, the episode immediately is terminated. Because sometimes it happens that the neural network doesn't learn at all, and it just gets stuck somewhere here in the valley. So if the agent ever reaches 5,000 time steps, the episode just gets restarted. Okay, so now on to the results. First, the on-policy versus the off-policy experiment. Remember, for this experiment, we are concerned about sampling observations from the buffer as if they were on policy or as if they were off policy. For the off policy agents, we're going to compute this importance sampling ratio, which we're going to use for computing the estimate of the return of Q sigma. Now, let's go first with Sarsa. I'm going to represent the off policy algorithm with a blue line and the on policy algorithm with a yellow line. Now, all the plots are going to follow this format. In the y-axis, we have the average return over the last 50 episodes. That means that if we are at a 100 mark, we're going to take the average from episode 51 to episode 100. These error bars right here are a confidence interval, a 0.95 confidence interval using a t-distribution. Yes?
Sorry, can you be more specific about the difference between on-policy and off-policy for Sarsa?
Yeah, so we can adapt Q sigma to use importance sampling in order to account for the difference in the policies, right? So off policy means that we're going to use that importance sampling ratio in order to account for that difference. On policy means that we are just completely going to ignore the difference in the 2 policies, and we're just going to compute the return as if it was on policy. And the reason why it should be off policy is because the observations in the buffer are sampled according to a different distribution than the one that we're using at time t. Is that?
You mean on-policy means you just ignore the problem?
Yeah, you just ignore the problem. Yes?
So in this plot, higher is better?
Yeah, thank you. I forgot to mention that. So yeah, in this plot, the higher the line goes, the better the algorithm is performing. In this case, we can see that. Zach?
Yeah, we can finish here.
Oh, okay. Sorry. So in this case, we can see that the on-policy Sarsa is just doing way better than the off-policy Sarsa. Significantly better, not just better. And well, my intuition for why this happened is because Sarsa on policy is using a bias estimate of the return. But even if it's biased, that estimate doesn't have as much variance as the estimate computed by the Sarsa of policy. Remember, the importance sampling ratio does correct for the difference in policies, but it also introduces a lot of variance for the estimate. So it seems like the variance induced by the importance sampling ratio is not enough to overcome the bias. I mean, sorry. Yes, that's what I meant. Sorry. Anyways, what happened with the rest? Oh, sorry.
Those are both using the same learning rate.
Yes, all of them. Every parameter that I'm not mentioning is using exactly the same hyperparameters.
So what do you think would happen if you tuned the learning rate for Sarsa off policy? Could you improve its performance?
They probably would improve a little bit. I wouldn't expect it to get better than Sarsa on policy. I feel like, Yes?
I didn't mean to interrupt you either, but is this a standard mountain car domain where minus 500 is actually pretty bad performance, or is minus 500 good?
Minus 500 is actually pretty bad performance.
Okay.
That's, yeah, it's going to get better as we move forward. So this is also one-step Sarsa, right? So it's using a neural network, which is a super difficult function approximator to work with. Yes?
Did you try retrace?
No, I didn't try retrace. Yes, sorry. Yep.
Sorry, comment. I think you're using absolute gradient policy, right?
Mm-hmm.
And if you do absolute gradient with importance sampling, that means when epsilon is very small, the importance ratio can be very high, and that might be the reason as
Yeah.
you keep learning performance drop down.
Yeah, certainly that's true. So maybe we used a different policy, that wouldn't be the case. I think before I go to Zina, what I wanted to emphasize is that Sarsa policy work. And this is doing nothing. This is basically ignoring the problem. I think that's what it should surprise us, because we're not trying to compensate for the bias, and it still works, which is not what we would expect. Zina, first?
I think it's, as Jacques said, I think it's really important to tune the step size for Sarsa policy, because Sarsa policy is, as you said, it's high variance, and you're setting the step size the same for our policy and our policy. It's just,
Yeah.
it's not fair to our policy.
Yes, you're definitely right. It's okay. I forgot to mention this is also average over 150 runs. So tuning the step size parameter and other hyperparameters, it wasn't actually an option in this case, because I run about 40 different agents for 500 episodes over 150 different runs. So yeah, I was planning on trying different alphas, but I think this is still kind of preliminary in that case.
Ignore my question. I want to see the rest. I've interrupted you too much.
Okay, so again, all the plots are going to follow the same format. Now, let's see what happens with Q sigma 0.5. Same thing. Off policy is doing really bad. On policy is doing really well. Not really well, but it's doing all right. Again, we might be able to tune alpha to make the off policy method work better. But again, tuning it implies a lot of computations. And if the on policy method already works pretty well, I don't see why tune alpha at all. Yes, of course, a more rigorous parameter study would be better, but this is what I have right now. Okay, so now what happened with Decaying Sigma? Now, surprisingly, Decaying Sigma was the other way around. The off-policy algorithm actually performed better than the on-policy one. And my intuition for this is because Decaying Sigma is only using the importance sampling ratio at the very beginning of the training. During that time, the estimates are all biased. The estimates have a lot of variance. So using the importance sampling ratio really doesn't hurt that much. It actually helps a little bit. Later on, by episode 100, Decaying Sigma is already expected Sarsa. At that point, it's not even using the importance sampling ratio anymore. So that's why the performance doesn't get affected anymore after that. That's my intuition of why it works. Honestly, it might be any other different reasons. Nico?
So for this study, you did not include expected Sarsa in the results.
Oh, for this one?
Did you run them?
Oh yeah, I run expected Sarsa, but the reason why I didn't include it in this experiment is because it doesn't use importance sampling. So that means we're not computing importance sampling ratio for expected Sarsa.
How did it go? How did it compare with this?
I'm going to get to that, yes. So okay, the next experiment. Annealing epsilon versus no annealing epsilon. In this case, if we anneal, we're going to store mu t. And if we are not annealing, we're just going to do on-policy, the on-policy method. The exploration frame is going to be 20,000 time steps. And after that exploration frame, the agent is basically behaving on policy, then on. So that means when epsilon hits the target, all the samples from the buffer are going to be sampled as if they were on policy. OK? Is that clear? Good. OK, so how does their results look like? Annealing is going to be green. No annealing is going to be red. And really, there's not much significance. Maybe with more runs, we will show that Sarsa without annealing is worse. but so far there doesn't seem to make any difference. We're going to see the same with Q sigma 0.5. There's no difference. With Expected Sarsa, there's no difference. With Decaying Sigma, really there isn't any difference. And with Q-learning, there's no difference. Now, this might be just because the mountain car environment is not a super complicated environment. We don't actually need to do a lot of exploration. There are only 3 actions that we can explore. So that's why I think annealing epsilon might not be doing that well. Now, what is interesting in this plot, though, Q-learning has some drop in performance sometime in the middle of training. And this is very similar to what happens in some of the games in the ALE, where halfway through training, Q-learning actually experiences some kind of drop in performance. I just found it interesting that this also happens in a more simple environment. I don't know if they are related. Maybe I'm just drawing random connections, but I just found it interesting. Now, Stian was asking, how do we compare? How does Expected Sarsa work against Q-learning? In this case, we are going to test both algorithms without annealing, and this is the plot. So Expected Sarsa is going to be pink, Q-learning is going to be violet, and this is how it looks like. So at the beginning, they are pretty similar, but at some point, Q-learning drops in performance and just does worse than Expected Sarsa, which is somewhat interesting. OK, so let's move to the next experiment, the n-step results. So I tested 5 different values of n. N equals 1 is going to be green. N equals 3 is going to be yellow. 5 is going to be orange. 10 is going to be pink. And 20 is going to be red. For Sarsa, this is how the results look like. Now, we're going to see this same pattern for many of the methods. At the beginning of training, having a longer return, a larger n actually helps performance. At the very end of training, however, it doesn't really make a lot of difference. As long as you're using anything higher than 1, it seems that all of them actually perform about the same. Again, this pattern is the same in Q sigma 0.5. Having a longer backup helps you at the beginning, but at the very end, it doesn't make a lot of difference. Same with tree backup, and with Decaying Sigma as well. And again, on every single plot, a larger than 1 n helps performance at the very end. OK, so since I already have all this data, we might as well compare how all these different algorithms perform. I'm going to judge best performance in terms of the average reward at the very end of training. Average return at the very end of training. So that means at the end of training, we take the average over the 500 episodes and the average over 150 runs, and then whichever has the highest number is going to determine to have the best performance. So for each of these algorithms, we just took whichever performed the best, whichever n performed the best. For Sarsa, it was n equals 10, and it's going to be represented with purple. For Q sigma 0.5, it was n equals 20, represented with pink. Tree backup was n equals 20, and Decaying Sigma was n equals 20. Now, I'm also going to plot Q-learning just as a baseline, just so that you can compare it with that one. So this is how the plot looks like. Again, here's Q-learning. Tree backup and Sarsa at the very end seem to be performing pretty similarly. And Q sigma 0.5 is performing the best among all the algorithms. Decaying Sigma, unfortunately, wasn't as good as I was hoping for. But it's interesting that Q sigma 0.5 is performing so well. Now, I was really disappointed with Decaying Sigma because I wanted to find the same, I wanted to see if we could find the same pattern as in the linear and tabular case. So I chose a different decay rate just to see what would happen. So I chose a decay rate so that at the middle of training, by episode 250, the sigma in Decaying Sigma was 0.5. So that means the decay rate is a little bit smaller. Sorry. Yes. Anyways, and this is what happens. The best n for this Decaying Sigma was n equals 10. And this is how the plot looks like now. So it seems that changing the rate does help the performance of Decaying Sigma a little bit. But in the end, it didn't manage to outperform Q sigma 0.5. However, it's interesting to see that if we decay sigma, we actually find the same thing as in the linear function approximation case, which is we can improve the performance of the algorithm. Yeah, and this is all for the results. So in conclusion, well, I successfully implemented, combined DQN and Q sigma, which is pretty useful. We find similar results in the nonlinear case as in the linear case and tabular case, and that is intermediate values of sigma sometimes perform better, and decaying sigma over time sometimes improve performance. And finally, the DQ sigma network managed to outperform DQN. However, it's also important to keep in mind that it was just mountain car. Like, it's a very simple environment. So there's a lot of work to be done if we really want to show that the DQ sigma, there's any merit to the DQ sigma in architecture, but this is a very good beginning for it. This actually shows promising evidence that we might expect better performance using the DQ sigma network in a more complicated environment. And that's it. Thank you. Okay, yeah?
For your environment, can you explain again what is your input feature to your network and what is your network architecture?
Yeah, so what I'm feeding to the network is just the position and the velocity of the car. The network architecture is just a feed-forward neural network with 1,000 neurons. It's like very simple. And then, yeah, that's it. It just outputs the the action value function for each of the actions.
So it's not really deep.
Yeah. I realized that after yes, it's.
For this, have you actually tried? Maybe you can use the exact architecture as DQN, but instead of inputting this position and velocity, you give the entire image to the network. I have done that experiment using the pole balancing test. It actually works pretty well. I don't know if that will work for mountain car too, but for pole balancing, you can just take DQN and input the image of it without having to give it the angle or anything. So.
Yeah, that's also a thing that we could do. Mostly I did mountain car because it's a very small environment and it's fast to run the Q sigma network architecture. Otherwise, might as well just go to the ALE, but it would take too long. And because I wanted to do so many different parameters, so I run about 40 agents and 150 runs for each of them. So otherwise, I wouldn't have been able to do all of this with the resources that I have available. Now, if anybody at Borealis or DeepMind would, I'm just kidding. Yeah. Any more questions, Martha?
Actually, I have lots of questions, but I'll just ask one.
No, you just go.
This is really cool results. I'll probably just come on to ask you offline. But for the graphs, did you do evaluation runs to get those lines, or did you plot the performance as the agent was going?
As the agent was going, like Marlo suggested in his revisiting their ALE paper, it's just as the agent is training, that's how I'm computing the average return. I'm not performing any kind of evaluation runs or anything. Nico?
So you have a slide where you move on to the best performance section, but
Yeah.
right before that you have graph. And I'm sorry, I don't remember what graph is.
Good. That one?
Yeah, so here you also have like a decreasing performance for n equals 1. But you didn't talk about that, so do you have any thoughts about it?
I really don't know. And actually, if we move, like all of these graphs kept the same, what's it called, scale, so that we could compare the results across graphs. But here, I'm actually plotting the best performance of the DQ sigma, decaying sigma agent. And we can see that it actually does show in a smaller scale, but it also shows a drop in performance, and then it goes back up. My intuition is that maybe decaying sigma might introduce some instability that hurts performance a little bit. But I take it with a grain of salt. I don't really know. Yeah. Zach.
So you said that your function approximator has 1,000 weights. Do you remember?
Yeah.
So how does that compare to like when we did tile coding?
Yeah, we did. So in the AAA paper, we did tau coding. It was about 6,300 weights. The network here has about 6,003 weights. So it's comparable in the amount of weights. So this neural network actually has less weights than the tau coder that we used in the AAA paper. Yeah.
Make one more comment. At the end, you said this is a simple result because it's just on mountain car, and mountain car is easy. But I might add that most of your results are now outperforming like really simplistic tau coders. Like the performance of these DQN agents, it's not saying that your algorithm is not good. Your algorithm has made the lines go from being noisy and ridiculous to actually looking quite reasonable, but it's still not necessarily getting fabulous performance.
Oh no, not at all.
So I'm saying that maybe it isn't a simple domain in that sense to explore some of these algorithms. It's not acing it, that's for sure.
Yeah, I just feel like reviewers would be like, the domain is simple, try it in the LE. I know. Because we got that when we submitted the AAA paper, we got like, oh, it's not deep. So it was like, well, what do you want me to do about it? Martha?
I have kind of a general question, and it's probably not just for you, but sort of for the community, because there are all these experiments that get a little late, on camera. A lot of these experiments, you get some results that maybe you don't expect them. But then how do you go and ferret out the reasons for these things, especially in the deep community? You know, they publish all this stuff, go, oh, I got this result, oh, great. Well, they have no idea why they got that result, but there's the result. And I'm not saying you do this.
Yeah.
But how do you go about figuring out exactly why some of these things perform the way they do? I mean, some of them you have hypotheses for, and others say, I have no idea. So how do you do that?
So for example, for the importance sampling ratio one, the one that I had like a better intuition of what was going on, in this case, I just assumed that the neural network was a black box giving me a value, and I just deal with the loss function to explain the effect that we observe here. The importance sampling ratio doesn't get used anymore after 100 episodes, so that's why the loss function changes. But for other results, like why Decaying Sigma has that performance right here, why it drops in performance, I really just,
and how do you go about figuring that out?
Yeah, that's a good question.
I mean, I'm not asking you to do it here, but it seems like a lot of times when we run these experiments, we get these odd behaviors, but it's not always easy to do it. And I don't know if the tools that you use, you can even look at almost like moment by moment what's happening with the algorithm, and then that may give you some intuition or tell you nothing. I have no idea. That's what I'm trying to ask. Yeah.
So I think the answer to that is some of that you print out everything that's going on, or you visualize it in some way, and you use small domains like this where it's even possible to do that. And something like a tire, you joke that there's just no hope of doing that. And in fact, you probably won't even see these differences. It'll just be a mush of all lines
All sorts of stuff.
wiggling everywhere.
Yeah. How would I go about, like, at least this problem right here? How would I go about analyzing it? Probably would first look at the loss function, see how it behaves, because these error bars are so wide, it makes me believe that there's a lot of variance in all of these runs. So for example, in the Q-learning case, like, I know that for a fact that a few of the agents just didn't learn. They just failed completely to learn, and that's why the error bars are huge. So in this case right here, also would believe that probably there's a lot of variance in how agents behave. As a comparison, here in Q sigma 0.5, the error bars are actually really, really, really small. Like even here at the very beginning of learning, the error bars are pretty small. That means that the agents are behaving about the same in every run. So what I'm thinking is like, it has something to do with the stability of the algorithm.
Because you're decaying the sigma, so it's probably taking more and more expectation at that point, and the value at that point might be actually very inaccurate, maybe. And if you're summing it way to sum of that, the target isn't as good.
Yeah, but also my intuition is like, well, neural networks don't like stuff moving around too much. That's why we use a target network. The decaying sigma thing makes it so that the target is changing all the time. So the neural network gets a different loss every time it samples from the buffer. And the problem with that is like, it just induces more instability. So that's my intuition for this kind of thing. Yeah. You?
Maybe we should cut it off now, just all go ask questions.
Oh, what time is it? Yeah. Okay. Yeah, just come to me after the talk.